What if the Big Bang was not the true beginning of everything? What if the moment believed to start space, time, matter, and energy was only the visible opening of a much older story? Tonight, this journey moves beyond the first light of the universe and into one of the deepest mysteries in science, what could have existed before the Big Bang. From quantum vacuums that are not truly empty, to strange cyclic models of the cosmos, to the possibility that our universe may have risen from the ashes of another. The deeper the search goes, the more incomplete the story begins to feel. Before the journey begins, thank you for being here and for spending time with this channel. If this kind of science speculation and cosmic mystery is interesting, please like the video, subscribe, and share it with someone who loves the universe as much as this audience does. It truly helps the channel grow. And as always, it would be lovely to know what time is it there, and where in the world is this being heard from tonight. Now, with that said, let us begin. For as long as human beings have looked upward, the beginning has remained both the brightest idea and the darkest gap. The sky appears full, but the story behind it opens into absence. There are stars burning in ordered patterns, galaxies turning in clusters, nebulae flowering with strange colour, black holes shaping their surroundings without showing themselves, and behind all of it a faint sea of ancient radiation that seems to whisper of a young universe, once far hotter and denser than anything that exists now. Yet the closer attention moves toward that early moment, the more the scene begins to thin, as if reality itself becomes less solid near its own source. What seems at first like a triumph of knowledge slowly changes into a confrontation with limits. The universe can be measured, mapped, timed, and compared. But the question of what truly comes first still stands untouched at the centre. Modern astronomy gives the impression of extraordinary reach. NASA and ESA place telescopes above the atmosphere so that the sky can be seen without the blur of air and weather. Hubble spends decades staring into deep space and reveals that even the blackest patch of sky is crowded with galaxies. James Webb peers farther through dust and farther back in time, catching light that has travelled for more than 13 billion years before arriving at its mirrors. Large observatories on Earth, from the Atacama Desert to volcanic mountain summits, track the red glow of remote galaxies and measure how fast the universe expands. The Planck mission maps the residual heat left from the early cosmos with astonishing precision. Everywhere instruments look, they find motion, structure, and history. The cosmos is not static. It changes, stretches, evolves, cools, and rearranges itself on scales so large that ordinary thought can barely keep hold of them. These measurements support the broad picture that modern cosmology knows best. The universe is expanding. Galaxies are not simply drifting through space in random directions. On the largest scales, space itself is stretching, carrying them apart. Their light shifts toward the red end of the spectrum, and that redshift becomes a kind of clock. The farther away a galaxy is, the longer its light has been travelling, and the younger the universe appears in that direction. By following this evidence backward, cosmologists arrive at a past state in which everything is compressed, hot, bright, and dense beyond ordinary comparison. This is the framework commonly called the Big Bang. It does not describe an explosion inside an already existing emptiness. In its standard form, it points instead to the early expansion of space itself. Matter, radiation, time, and distance all emerge within that unfolding. The universe does not expand into a waiting room. The room is part of the event. That idea carries tremendous explanatory power. It helps account for the abundance of light elements such as hydrogen and helium. It fits the existence of the cosmic microwave background. the afterglow of a time when matter and light finally separate and space becomes transparent. It matches the large-scale arrangement of galaxies across the observable universe. It gives cosmology a timeline that stretches from the first instance after the beginning through the formation of stars, galaxies, planets, and the heavier elements forged inside stellar cores. It allows a coherent picture of cosmic history to exist at all, but it is not a finished story, and the closer it approaches the beginning, the more its confidence weakens. A quiet misunderstanding often hides inside popular descriptions of the Big Bang. Many imagine a single point of infinite density suddenly bursting outward into darkness. That picture is simple, vivid, and deeply misleading. Physics does not actually handle infinity well. When equations yield infinite density and infinite temperature, that result usually means the theory has reached a boundary beyond which it can no longer be trusted. In the case of the early universe, general relativity works with immense success across stars, galaxies, and cosmic expansion. But near the beginning it collides with the quantum world, where uncertainty and fluctuation dominate. The equations point toward a singularity, yet the singularity may be less a physical object than a sign that the map ends there. What lies beyond that edge remains hidden, not because nothing is there, but because the known tools begin to fail. This is where the mystery deepens. Science can describe the universe when it is already changing, but the instant that would explain why there is a changing universe at all appears increasingly difficult to reach. The first fractions of a second are reconstructed with mathematical care, yet each earlier layer removes another piece of ordinary intuition. At later stages, plasma fills space, particles collide, atoms have not yet formed, and radiation rules the young cosmos. Earlier still, even protons and neutrons are not yet stable. Earlier again, the known forces of nature may behave as one. Eventually cosmology arrives at a threshold so remote and so extreme that the familiar ideas of place, duration, and sequence begin to lose their ordinary meaning. There is still physics there, perhaps, but not physics in the form human beings experience in everyday life. The beginning starts to look less like an event within time, and more like the source from which time itself becomes possible. Even the language used around this subject can quietly mislead. Questions such as what happened before the beginning sound clear at first, yet the word before assumes time is already running. If time itself emerges with the early universe, then asking what comes before may be like asking what lies north of the North Pole. The grammar survives while the meaning slips, and yet the question refuses to die, because the human mind senses that a boundary described only by silence is not yet an explanation. If space begins, what allows it to begin? If time begins, what grounds that transition? If matter and energy appear in a hot young cosmos, what carries the possibility of such appearance in the first place? The standard model of cosmic expansion answers many questions magnificently, but it leaves the deepest one standing in the doorway. This is why each discovery often increases the unease rather than removing it. Hubble sees farther, and the early universe appears populated sooner than expected. James Webb reveals surprisingly mature galaxies in cosmic youth, and astronomers are forced to rethink how quickly structure can form. Measurements of expansion lead to tensions between different methods, hinting that some ingredient in the larger picture may still be missing. Dark matter shapes galaxies through gravity, yet remains invisible to direct detection. Dark energy seems to drive cosmic expansion faster over time, though its nature remains obscure. Even the universe now in view is full of hidden components. In that setting, it becomes difficult to believe that the first moment is fully understood. The known universe already contains absences within presence, invisible forces inside visible order. the beginning may be no different. At the largest scale, the cosmos appears strangely balanced between simplicity and strangeness. On one hand, a few elegant principles describe much of its behavior. Gravity gathers matter, expansion spreads space, nuclear processes ignite stars, light travels finite distances and preserves history. On the other hand, every successful explanation opens a deeper uncertainty below it. Why do the laws have the form they do? Why do the constants permit stars, chemistry, and long cosmic evolution? Why does the universe begin in such a low entropy state, ordered enough for complexity to unfold? Why does it contain anything at all rather than remaining in perfect absence? These are not decorative questions added after the science. They emerge from the science itself, from the very success of tracing the cosmos backward to a state where ordinary explanation begins to dissolve. So the search moves forward by moving deeper into the past. It studies ancient light, elemental ratios, the growth of galaxies, the warping of space, and the behavior of the vacuum. It builds a picture of the universe not as a finished machine but as an unfolding puzzle. The old hope is that enough observation will eventually close the gap. The newer and more unsettling possibility is that the gap marks not a missing measurement, but a transformation in the meaning of reality near its source. The Big Bang may still be real, but not complete. It may describe the visible opening of the story without revealing what prepares that opening. It may tell how the universe develops once expansion is underway, while saying almost nothing about what allows such a beginning to happen. And as the evidence grows more precise, that missing layer begins to feel less like a small technical omission and more like the central mystery itself, waiting behind the first light, silent, patient, and older than time. The first surprise in any careful history of the universe is how late familiar matter arrives. Stars, planets, rock, water, metal, air, and living bodies all seem basic from the human point of view, yet none of them belong to the earliest chapter. Even atoms, the quiet building blocks of ordinary substance, are absent at first. The young cosmos begins not as a place filled with formed things, but as a changing state of energy so intense that stable structure cannot hold. Temperature is not simply high. It is so extreme that what later becomes ordinary matter exists only as a restless storm of more elementary ingredients. The deeper the timeline moves toward the opening of the universe, the less the world resembles anything solid, and the more it starts to behave like a field of transitions without permanence. In the first broad outlines of cosmic history, the sequence appears deceptively clear. The universe expands and cools. As it cools, different forms of order become possible. Forces that may once have been joined take on separate roles. Particles interact, disappear, reappear, and settle into more durable forms. Much later, atoms emerge. Later still, gas gathers under gravity into the first stars. Those stars forge heavier elements, explode, enrich space, and make possible the chemistry from which planets and eventually life can arise. It is an elegant progression, almost too elegant, because once it is laid out this way it can feel inevitable. But that feeling fades as soon as the clock is turned backward in detail. For hundreds of thousands of years after the beginning, the universe remains opaque. Light exists everywhere, yet cannot travel far without colliding with charged particles. Space is filled with a hot plasma, a sea of nuclei and electrons not yet bound into neutral atoms. This glowing fog hides the deeper past from direct sight. Only after enough cooling does matter become calm enough for electrons to join nuclei and form stable atoms, mostly hydrogen and helium. At that point, light finally begins to move freely through the cosmos. The ancient radiation that still washes across the universe today comes from this release. long after the first instant, long after the earliest violence, long after whatever truly sets the beginning in motion. What modern instruments detect as the oldest visible light is therefore not the first light in any absolute sense. It is only the oldest light that survives the transition from opacity to transparency. Behind it lies an earlier age that cannot be seen directly in the same way. Even before atoms appear, the universe passes through another threshold in which the first light nuclei form. This process, known in plain language as primordial element making, happens within the first few minutes. Conditions are briefly suitable for protons and neutrons to combine into the nuclei of hydrogen, helium, and traces of lithium. Then the cosmos expands further, density falls, and the window closes. The result is a universe whose basic chemical recipe is set astonishingly early. Much later stars refine that recipe, but they do not create the first pattern from nothing. The young universe already leaves behind a clear signature of its opening conditions. This is one reason the Big Bang framework remains so powerful. It predicts a cosmic ancestry written into the matter still present today. Yet even here a shadow remains. Protons and neutrons themselves have a history, and that history leads into stranger territory. Go farther back, to less than a second after the beginning, and stable atomic nuclei do not yet exist. Matter as common experience understands it as not assembled. Protons and neutrons are only beginning to emerge as durable combinations of more fundamental particles. Before this, the universe is dense and hot enough that quarks, the constituents later locked inside protons and neutrons, are not confined in the familiar way. They move within a seething environment alongside other short-lived particles and intense radiation. The cosmos at this stage does not contain objects. It contains processes. Things do not persist long enough to deserve the names they later receive. Existence is defined by transformation. Then the timeline pushes earlier still, into a fraction of a second so small that ordinary language begins to falter. Physicists describe an epoch in which the electromagnetic force and the weak nuclear force are not yet distinct in the way later experiments reveal them. Some theories go further and suggest that at still higher energies even more of the fundamental forces merge into a single description. This possibility carries enormous weight, because it implies that the universe begins with greater unity than it later shows. The variety seen now may be the cooled, broken, differentiated form of an earlier simplicity. But that simplicity is not easy to picture. It is not a smooth crystal of perfect order. It is a realm of such extreme energy that the categories used to describe matter, radiation, and interaction start to overlap. The universe grows simpler in one sense and less intuitive in another. The mystery sharpens when matter meets antimatter, according to known physics. The early universe should produce both in almost equal amounts. For every particle there exists an opposite partner of the same mass but reverse charge or related properties. When they meet, they annihilate into energy. This is not a rare event in the young cosmos. It is one of the central rhythms of that early environment, a constant conversion between being and radiant release. If exact symmetry ruled completely, matter and antimatter would erase one another almost perfectly, leaving behind little more than light. And yet a tiny excess of matter survives. Everything visible now, every galaxy, star, planet, and living thing, depends on that imbalance. Somewhere in the early universe, a minute asymmetry appears. It is one of the quietest and most consequential anomalies in all of cosmology. The known universe exists because matter wins by the narrowest margin imaginable. The reason for that victory remains uncertain. This is where the beginning starts to acquire a peculiar character. It is not only hot and dense, it is selective. It permits some structures to stabilize while others vanish. It favors a slight difference that later becomes everything. A cosmos perfectly balanced between matter and antimatter would look profoundly different from the one observed today. The visible universe therefore carries evidence of an early decision, though decision is only a metaphor. Something in the laws, or in the initial conditions, or in quantum behavior during extreme energies, produces an uneven outcome. The early universe is not just a furnace, it is a filter. Tracing this filter backward leads naturally to the question of what counts as matter in the first place. Ordinary speech treats matter as the obvious opposite of empty space. A stone occupies space. A star contains mass. A body has substance. But the early cosmos does not honor those common distinctions. Stable matter is late, before atoms, before nuclei, before protons and neutrons. What exists is a set of fields and excitations, relationships and transformations. Matter does not emerge fully formed from the first instant. It condenses out of a more primitive state. This fact matters because it changes the emotional shape of the original mystery. The old question asks how matter comes from nothing, but physics keeps uncovering layers in which matter itself is not fundamental. The true puzzle retreats deeper. It becomes a question not about chairs and stones or even atoms and nuclei, but about how any physical state capable of producing structure comes to exist at all. The deeper the account goes, the more the universe resembles a transition between regimes rather than the appearance of a finished world. One stage gives way to another as temperatures fall, symmetries break, particles acquire mass through interactions with underlying fields. Stable arrangements emerge only because instability slowly eases. In that sense, the beginning is not a single flash but a series of thresholds, each one making the next level of reality possible. The first atoms wait for cooling. The first nuclei wait for the right density and timing. The first durable particles wait for a shift in the conditions of the young cosmos. But each threshold raises a quieter and more dangerous question. What sets the first threshold? What determines the starting conditions from which all later transitions follow? At very early times, cosmologists can still write down equations and test some consequences against observation. The expansion rate affects the relic radiation. The balance of particles influences the abundance of light elements. Subtle features in the large-scale pattern of galaxies preserve traces of the early universe. These are not vague impressions, they are measurable relics, yet they only confirm that the universe once passes through exotic states. They do not fully explain why such states exist in the first place. The trail grows firmer and stranger at the same time. The more detailed the timeline becomes, the more clearly it shows that familiar reality is built in stages from something far less familiar. But every step backward also removes another piece of certainty. Stable matter dissolves into unstable ingredients. Distinct forces blur into possible unity. Symmetry briefly reigns and then breaks. The first chapter no longer looks like a beginning in any simple sense. It looks like the visible crest of a much deeper process, one whose lower layers remain hidden below the line where matter first learns how to stay. If the search for the beginning stops at matter, it ends too early. Matter is only one phase of the story, and not the oldest. Beneath particles, beneath atoms, beneath the hot plasma of the young universe, modern physics finds something even stranger, fields filling space at all times, whether anything visible is present or not. These fields are not decorative background. They are the deeper framework from which particles arise as localized disturbances, brief ripples, temporary knots of energy that appear stable only under the right conditions. This changes the meaning of emptiness in a profound way. What appears to be vacant space is not a silent void waiting for events to enter it. It is an active stage already holding the possibility of events within itself. And once that is understood, one of the oldest assumptions about the universe begins to fail. Nothingness becomes harder to locate. In ordinary life, empty means cleared out. A room without furniture is empty. A road without cars is empty. A black night sky between stars seems empty. But every increase in scientific precision has weakened this simple image. Even the space between galaxies contains thin gas, drifting particles, magnetic traces, and radiation. More importantly, the very vacuum of physics, the lowest energy state a field can occupy, is not equivalent to absolute nothing. It is the least excited version of a physical system, not the absence of system itself. This is why the vacuum behaves in ways that classical intuition never expects. It fluctuates, it stores energy, it influences particles that move through it. Under the right conditions, it can even produce effects that look disturbingly close to creation from emptiness. Quantum field theory, the framework that describes particles and their interactions with remarkable accuracy, treats every kind of particle as tied to an underlying field spread through all of space. An electron is linked to one field, a photon to another, quarks to others still. What is called a particle is not a tiny billiard ball hidden somewhere in the field. It is an excitation of that field, a detectable event, a concentrated expression of something more diffuse and more fundamental. The vacuum is therefore not the absence of fields. It is the state in which those fields are not excited in the ordinary, lasting way that produces stable particles. But even then, they do not remain perfectly still. This restless behavior is one of the strangest ideas in modern science, yet it is not mere fantasy. Quantum theory allows brief fluctuations that momentarily produce particle-like events before they vanish again. These are often described as virtual particles, though that phrase can mislead because it sounds unreal. The effects associated with such fluctuations are very real. They influence measurable quantities and leave fingerprints in experiment. In certain situations, the vacuum behaves as though pairs of particles emerge for a moment and then destroy one another before becoming part of the lasting world. Something appears, then disappears. Presence flickers inside absence. The universe, even when stripped to what seems like its bare minimum, refuses to become still. This does not mean that science has proved something literally comes from nothing. The vacuum is not nothing. It is already a physical arena governed by laws, structured by fields, and capable of fluctuation. Yet the emotional force of the phenomenon remains powerful. At the edge of emptiness, the world seems unstable in a creative way. Reality does not merely occupy space. It threatens to appear wherever space exists. The difference matters because many popular accounts blur the line between vacuum and nothingness, turning a subtle scientific point into a stronger claim than the evidence supports. Still, even when the distinction is preserved carefully, the mystery only shifts deeper. If the vacuum is not nothing, then what is it? Why do these fields exist at all? Why should empty space have properties? The answer grows stranger when gravity enters the picture. In laboratories and particle accelerators, quantum fields can be studied within an already existing space-time background. The stage is taken for granted. Space and time are there first, and fluctuations happen within them. But cosmology cannot remain satisfied with that arrangement, because it is trying to understand the universe as a whole. If the question concerns the earliest reality, then the vacuum cannot simply be placed inside a pre-existing cosmos, as though the larger setting needs no explanation. One must ask where space-time itself comes from, and whether the vacuum depends on it, or helps generate it. The moment this question is asked, the ground shifts again. The restless vacuum that once seemed close to the beginning now becomes part of the thing requiring explanation. There are hints from several directions that empty space possesses more structure than older physics imagines. One of the best-known examples comes from what is called the Casimir effect, in which two extremely close conducting plates alter the allowed fluctuations of the vacuum between them, producing a measurable force. The effect is subtle, but it demonstrates that vacuum behavior is not philosophical decoration. It has consequences. In other contexts, intense fields near black holes suggest even more dramatic possibilities. According to Stephen Hawking's famous insight, black holes are not perfectly black. Quantum effects near the event horizon can lead to a slow leak of radiation, allowing the black hole to lose mass over immense spans of time. Here again, what seems like nothingness near an invisible boundary becomes physically productive. The darkest regions of the universe do not remain mute. Even they may whisper energy away. This idea matters for the beginning because it softens the ancient divide between being and non-being. Reality no longer appears as a fixed inventory of things sharply separated from a separate background of emptiness. Instead, it behaves like a layered continuum in which the background itself has properties, and those properties can produce phenomena. Existence becomes less about solid objects resting in space, and more about excitations within a deeper order. Once that shift occurs, the question of origin changes form. It is no longer only how objects arise, it becomes how a lawful, active, fluctuation-rich backdrop comes to exist, and whether that backdrop is itself emergent from something deeper still. Cosmologists have long noticed that the early universe seems especially sensitive to vacuum-like energy. The idea of cosmic inflation, though not the focus of every origin model, proposes that a brief episode of extremely rapid expansion occurs in the first tiny fraction of a second. In many versions of the theory, this expansion is driven by a field occupying a high-energy state, something vacuum-like in the sense that it fills space uniformly and carries pressure unlike ordinary matter. Inflation helps explain why the observable universe looks so smooth on large scales, why distant regions share similar temperatures despite seeming too far apart to have exchanged signals in ordinary time, and why tiny fluctuations later become the seeds of galaxies. The remarkable implication is that the great structures of the universe may trace back to minute quantum irregularities stretched across cosmic distances. Vast galactic patterns could begin as microscopic tremors in a primordial field. The visible universe would then be the amplified memory of vacuum unrest. This is where the story becomes both clearer and more eerie. The vacuum is not merely a passive minimum, it can shape the history of everything. Tiny fluctuations may grow into galaxy clusters. Fields filling space may determine the masses of particles. Symmetry breaking in the early universe may lock in the laws later experienced as permanent. The universe begins to resemble a place where emptiness is creative, under rules that remain partly hidden. And yet every time this creative emptiness seems close to becoming an explanation, it slips away. Inflation may describe a phase of explosive early expansion, but what sets up the inflating state? Quantum fluctuations may seed structure, but what defines the field that fluctuates? Vacuum energy may drive behavior, but why does the vacuum have that energy? The same pattern repeats. Each level explains a higher one while exposing its own unknown foundation. Dark energy deepens this unease in the present era. Observations of distant supernova near the end of the 20th century suggest that cosmic expansion is not slowing under gravity alone but accelerating. Something acts on the larger scales as though empty space contains a persistent outward influence. The simplest interpretation links this to vacuum energy, though the observed value is bewilderingly small compared with naive theoretical estimates from quantum field calculations. This mismatch is one of the great unresolved puzzles in physics. Empty space appears to possess energy, but not in the amount expected. The vacuum is active, yet its measured cosmic role and its calculated microscopic possibilities do not align in any comfortable way. Even now, long after the universe becomes transparent, long after stars and galaxies form, emptiness remains an unsolved force. The beginning therefore looks less like a moment when matter suddenly appears in a blank void and more like a transition in a hierarchy of hidden structures. Matter emerges from fields. Fields fluctuate in vacuum states. Vacuum states influence cosmic expansion. Space-time itself may be entangled with the behavior of those fields at energies no experiment can yet fully reproduce. Nothingness retreats each time science approaches it. First, the empty sky is shown to contain galaxies. Then the space between galaxies is shown to contain radiation and particles. Then the vacuum itself is shown to teem with potential activity. At every stage, absence proves more complicated than it appears. This does not remove the mystery. It sharpens it. If absolute nothing is nowhere to be found in physics, then perhaps the universe never rises from literal non-being at all. Perhaps it emerges from states so minimal, so symmetrical, or so unlike ordinary experience that they only seem like nothing from a human perspective. That is one possibility. Another is even stranger, that the search for nothingness fails because reality is fundamentally unable to remain empty. The laws may be such that what can exist eventually does exist, that the vacuum cannot help but fluctuate, that instability is built into the floor of being. This remains speculation, but it grows naturally from the evidence that the cosmos is not content with silence. Even its quietest layers stir. So the investigation moves deeper still. It studies the behavior of the vacuum, the nature of quantum fields, the role of inflation, the energy of empty space, and the strange way fluctuations leave permanent scars on the cosmos. These are not side notes to the origin story. They are the origin story as far as present understanding can responsibly go, and yet they stop just short of the final question. The vacuum is not nothing, but why is there a vacuum? The fields are not nothing, but why are there fields? The laws allow fluctuations, but why do those laws hold at all? The closer the universe draws to its bare framework, the more that framework itself begins to look like the real mystery, hidden beneath the flicker of virtual particles, beneath the first plasma, beneath the earliest light, waiting in the depths where emptiness itself is never truly empty. There is a point in the backward journey where even the idea of a journey begins to fail. Earlier stages of the universe can still be imagined as a sequence. First the plasma, before that the particle storm, before that the brief intervals in which the familiar forces may not yet be fully separate. But when the timeline approaches the smallest meaningful interval known in modern physics, the old language of earlier and later starts to loosen. This threshold is often associated with what physicists call the Planck era, the region so close to the beginning that ordinary theories no longer fit together. General relativity describes gravity and the large-scale structure of space-time with extraordinary success. Quantum mechanics governs the small, the fluctuating, the uncertain, with equal power. Yet here, at the deepest edge of the early cosmos, both are needed at once, and in their current forms they do not fully agree. The result is not merely a missing detail. It is a breakdown in the known grammar of reality. To understand why this matters, it helps to notice how much of ordinary explanation depends on stable space-time. A cause happens somewhere, an effect follows later. Distance separates one event from another. Motion carries matter from place to place. Clocks tick. Paths can be drawn. Even the most abstract physics usually depends on some version of this stage. But near the beginning, density and energy rise so far that gravity itself becomes quantum in character. Space-time, which in relativity behaves like a smooth geometric fabric, may no longer remain smooth at all. It may fluctuate. It may foam. It may fragment into structures that are nothing like the calm arena later inhabited by stars and galaxies. If this is true, then the beginning is not simply a hot version of the universe now known. It is a domain where the stage and the actors are tangled together so completely that the distinction between them begins to disappear. This is one of the most unsettling ideas in all of cosmology. Human intuition expects that things happen in space and time. The Planck regime suggests that space and time themselves may be products of something deeper. They may be emergent, which means they arise from underlying relations the way a wave arises from water. A wave has shape, speed, and direction, yet none of those properties exist separately from the deeper medium beneath it. In the same way, the smooth space-time of common experience may be the large-scale appearance of microscopic processes too strange to picture directly. If that is the case, then the beginning cannot be understood by asking only what happened at the first moment. One must ask how moments become possible at all. Several major approaches to quantum gravity attempt to face this problem, though none has yet achieved decisive confirmation. String theory proposes that the most basic ingredients of reality are not point particles, but tiny vibrating entities whose different modes give rise to the particles later observed. In many forms of this framework, extra dimensions beyond the familiar three of space and one of time are also involved, though hidden from everyday perception. Loop quantum gravity takes a different path and suggests that space-time itself may have an atomic structure, built from discrete units rather than being perfectly continuous. Other approaches explore causal networks, holographic principles, or geometries emerging from entanglement. These ideas differ sharply in method and interpretation, but they share one deeply important suggestion. The reality beneath ordinary space-time may not resemble a smaller version of the world. It may be something structurally different, something from which the smooth universe is distilled. Once this possibility is taken seriously, the beginning grows more mysterious in a new way. Earlier sections of cosmic history already show matter dissolving into more basic ingredients. Now even the arena of existence dissolves. Time becomes less secure. Causality becomes uncertain. The phrase "what came before" begins to tremble, because before depends on time already being there. Likewise, the phrase "where did it happen" becomes unstable, because where depends on space already being present as a measurable background. The most natural questions remain emotionally compelling, yet their basic terms may no longer apply. This does not mean the questions are worthless. It means they are aimed at a layer of reality for which human language evolved no reliable instincts. There is a temptation to treat this limit as final silence, as though physics simply stops and all thought must end. But the situation is subtler than that. Physics does not become meaningless near the beginning. It becomes incomplete. There may still be lawful structure in the Planck regime, still a definite underlying order, still a describable precursor to the expanding universe. What disappears is not reality itself, but the easy compatibility of the theories used to describe it. This is why cosmologists and theoretical physicists continue working at the border. They are not staring into pure emptiness. They're trying to infer the shape of a hidden level of existence from the traces it leaves behind in the universe that follows. Those traces may be faint, but they matter. The early cosmos appears remarkably smooth on large scales, yet not perfectly smooth. Tiny variations in density exist, and these become the seeds from which galaxies later grow. Inflation, if it occurred, may have stretched quantum fluctuations to cosmic size. Certain models of quantum gravity suggest subtle imprints in primordial gravitational waves, slight deviations in the statistical pattern of the cosmic microwave background, or minute effects in the earliest distribution of matter. So far, nothing has provided a universally accepted window into the Planck regime itself, but the hope remains that the beginning is not wholly sealed. The universe may still carry scars from its deepest phase. too delicate to be read clearly now, but not erased. Even so, the conceptual difficulty remains immense in everyday experience. Causality feels absolute. One thing leads to another. This confidence has great practical value, but it may not survive unchanged at the foundation of the cosmos. If time emerges from something deeper, then causal order as it is normally understood may also emerge only at larger scales. Beneath it there could be more primitive relations, structural constraints, or patterns of possibility that later appear to beings inside the universe as temporal cause and effect. This is not an excuse to abandon reason. It is an attempt to reason more carefully at a place where ordinary categories may be consequences rather than premises. The beginning would then not be uncaused in the crude sense, but not caused in the familiar sense either. It might be grounded, generated, or realized by deeper physical order without occurring as an event inside pre-existing time. That distinction is easy to state and difficult to feel. Human thought is so attached to sequence that any origin not framed as an earlier event producing a later one seems almost unreal. Yet physics has repeatedly forced broader conceptions of reality whenever ordinary intuition proved too narrow. Earth is not the center of motion. Time does not flow equally for all observers. Particles do not always possess definite classical properties before measurement. Space is not merely an empty box. It would not be surprising if the deepest origin of the universe demanded another such expansion of understanding. The discomfort may not be a warning sign of error. It may be evidence that the mind is approaching a domain built on rules unlike those of daily life. There is also a more haunting possibility. The failure of current theories at the earlier scale may not be merely technical. It may reveal that the demand for a final physical explanation has a structure stranger than expected. Each layer of explanation so far has replaced solid objects with deeper processes. Matter becomes fields. Empty space becomes active vacuum. Space-time itself may become emergent geometry. If the pattern continues, the beginning may never appear as a simple first fact. It may always resolve into another underlying layer, one more abstract and less picturable than the last. In that case, what seems like a boundary may actually be a transition between descriptions, and the origin may lie not at a point but in a change of level. The first moment would then be less like the start of a story, and more like the moment a hidden code renders a visible world. Some speculative models attempt exactly this kind of move. In certain approaches, the universe tunnels from one quantum state to another. In others, a prior contracting phase rebounds into expansion. In still others, space-time emerges from entanglement patterns in a more fundamental quantum system. These proposals are not equally supported, and none has won the field. But their shared instinct is revealing. Again and again, the beginning resists being treated as a naked singular instant and instead appears as the visible edge of a deeper physical process. The universe may not erupt from literal nothing. It may condense out of a regime in which ordinary distinctions between geometry, energy, and law are not yet separated. That possibility changes the atmosphere of the mystery. The early universe is no longer just hidden by heat or distance. It is hidden by a change in the rules of intelligibility. Observatories can see far back, but not through opacity. Equations can trace the expansion, but not cleanly beyond the point where gravity becomes quantum. Thought can ask what comes before, but the meaning of before begins to fail. The beginning remains close in one sense, because everything comes from it, but unreachable in another, because the forms of reasoning used inside the universe may depend on structures that only appear after the beginning is already underway. And so the search pauses at a boundary that is not empty but unstable, not silent but untranslated. Something physical may be happening there, perhaps something far richer than the singularity image suggests. Yet the deeper the inquiry goes, the more the universe seems to guard its source by changing the very conditions under which questions can be asked. Time may be born rather than given. Space may crystallize rather than simply exist. Cause may emerge rather than rule from the start. If so, then the first true mystery is not merely what the universe contains, or even what event begins it, but how the framework of events, places, and durations rises from a more hidden order. Beyond that threshold, the cosmos grows dim, not because there is nothing there, but because reality itself may still be learning how to become a world. One of the strangest ideas to emerge from modern cosmology begins not with fire, but with exhaustion. It imagines a universe that has already spent nearly everything it has. Stars have long since burned through their fuel. Galaxies have drifted farther apart under accelerating expansion. The brilliant age of structure has faded into extreme thinness. Black holes, once the last great monuments of concentrated matter, slowly evaporate over inconceivably long spans through quantum effects first described in the 20th century. What remains is not a dramatic ruin, but a quiet, almost featureless emptiness, cold, dilute, and nearly lightless. At first glance, this looks like an ending so complete that no new beginning could ever emerge from it. Yet one speculative framework turns that very emptiness into the doorway of another cosmos. In that proposal, the end of one universe does not merely resemble nothing. Under a deeper mathematical view, it becomes inseparable from the beginning of the next. This is the territory of conformal cyclic cosmology, the controversial vision associated with Roger Penrose. It does not ask the universe to reverse direction in a classic collapse. It does not require a dramatic crunch in which all matter falls back together into one crushing point. Instead, it begins with an observation about scale. In daily experience, size matters. A grain of sand and a mountain are not equivalent. A tiny hot region and a vast cold expanse seem opposite in every meaningful sense. But Penrose asks whether there are conditions so extreme that size loses its usual importance. If the particles that possess rest mass are gone, if the universe is populated only by massless radiation or states that effectively behave that way, then the distinction between enormous and tiny may no longer carry the same physical meaning. The geometry can be stretched or compressed without altering the essential form of certain relationships. What looks infinitely old, cold, and large from one perspective may be mathematically transformable into something that looks young, hot, and small from another. This is not an easy idea because it runs against every ordinary instinct. The future of an aging cosmos seems emotionally opposite to the birth of a new one. One is thin, dim, and emptied of structure. The other is dense, bright, and violently fertile, yet conformal transformations. The mathematical reshaping central to Penrose's picture preserve angles and structure while discarding absolute size. In that language, two states can be deeply related even when one appears enormous and sparse, while the other appears compressed and energetic. The shocking suggestion is that the remote future of one cosmic age, stripped of all meaningful scale, can be joined to the Big Bang of another age as though they are different readings of the same boundary. To see why Penrose takes this possibility seriously, it helps to return to the fate of matter. In his picture, as the universe ages, ordinary matter becomes less central. Stars die. Matter falls into black holes. Black holes themselves are not permanent. Through Hawking radiation, they slowly lose mass and eventually disappear. If the universe continues expanding and all massive particles either decay or become irrelevant at extreme scales, then what remains is a state dominated by radiation and an almost perfect absence of structure. In such a world, Clocks built from massive objects lose their meaning. Distances measured by standard rulers lose their meaning. The cosmos is not nothing, but it has become so emptied of the features that define scale in ordinary physics that the notion of absolute size begins to loosen. This is the conceptual opening through which conformal cyclic cosmology enters. In this framework, each cosmic era, which Penrose calls an aeon, begins with something recognizable as a Big Bang and ends in an almost empty, ever-expanding future. But the end of one aeon is not simply followed in time by the start of the next. The relation is stranger than succession. The late universe, after enough erasure of mass and structure, can be mathematically reinterpreted as the boundary condition of a new hot beginning. The young universe is not caused by the old one in the usual sense of one event pushing another along a timeline. Rather, the old universe becomes the geometric basis from which the new one emerges when size and duration lose their ordinary roles. The line between ending and beginning is no longer a wall. It becomes a transformation. This matters because it offers one of the most imaginative physical responses to the ancient question of what comes before the Big Bang. Instead of asking for a prior event inside time, conformal cyclic cosmology suggests that the before is a previous cosmic age whose remote future is linked to the new beginning by a shift in description. The Big Bang is still a beginning for the universe as currently experienced, but it is not a beginning from absolute nothing. It is a rebirth from an older and almost emptied physical reality. That older reality is not familiar matter arranged differently. It is matter nearly erased, scale nearly dissolved, time stretched toward irrelevance. In that sense, the next universe arises not from fullness and not from literal nothing, but from a kind of exhausted physical residue so stripped down that it begins to resemble nothing from one angle and everything from another. The attraction of the theory lies partly in this elegance. It avoids the need for a first cycle with no explanation behind it. It replaces the one-time beginning with a sequence in which each cosmic era hands its final condition to the next. It also draws power from a certain philosophical economy, without having to become philosophy. Instead of asking why a singular universe appears once, it imagines a continuity in which origin is folded into long-term fate. The cosmos becomes self-propagating through structure rather than through external intervention. Yet the same features that make the theory alluring also make it difficult to test and easy to doubt. A theory about earlier aeons cannot rest only on elegance. It must confront observation. Penrose and collaborators therefore look toward the oldest radiation visible in the present universe, the cosmic microwave background, for possible relics of events that might have occurred in the previous aeon. The hope is that violent processes in that earlier universe, especially the final evaporation or activity of supermassive black holes, could leave subtle signatures carried through the conformal boundary into the new cosmic age. These signatures would not look like ordinary objects. They would appear as unusual patterns in the residual glow of the early universe, perhaps circular features or anomalous temperature arrangements difficult to explain by standard cosmology alone. Some analyses have claimed hints of such structures. Others have challenged those claims, arguing that the patterns are no more than statistical accidents in noisy data. The disagreement remains unresolved, and that unresolved state is important. Conformal cyclic cosmology is not established fact. It remains a provocative possibility pressed against the edge of available evidence. Still, the theory carries a deeper fascination beyond the immediate dispute over data. It changes the emotional logic of cosmic history. In the standard picture, the far future often feels like a terminal fading, a movement toward maximum dilution and loss of structure. The story begins with blazing intensity and ends in near silence. Penrose's view converts that silence into hidden fertility. The cold end state is not merely a tomb. It is a condition in which the meaning of scale falls away, allowing a new young universe to stand in continuity with the old. This transformation makes the end less final and the beginning less isolated. It suggests that the universe may not have one birth at all. It may be part of a chain of births, each one arising from the stripped remains of an earlier cosmic age. Yet this raises questions as quickly as it answers them. If each aeon leads to another, is the chain endless? Has the cosmos been passing through such transformations forever? Or is there some deeper principle that allows only a finite number of cycles? If the late universe must be emptied of mass for the conformal connection to work cleanly, do all forms of matter eventually disappear? What of dark matter, whose true nature remains uncertain? What of dark energy, which already shapes the long-term expansion and may not fit comfortably into every version of the scenario? A theory of cyclical rebirth cannot avoid the hidden contents of the cosmos, and those contents are still only partly understood. The universe today is already filled with invisible components. Any account of its far future must inherit those uncertainties. The theory also asks for a change in perspective toward time itself. In common thought, beginnings and endings stand apart because time flows in one obvious direction. A beginning opens possibility, an ending closes it. But in conformal cyclic cosmology, the distinction between these states is not erased by reversing time. It is reinterpreted through geometry. The beginning of one eon and the end of another belong to different temporal descriptions, and the bridge between them is not a conventional duration that an observer could traverse. There is no final witness standing in the cold last universe and then watching the next Big Bang appear after a waiting period. The two regimes connect more like matching edges in a deeper mathematical fabric. That is why the theory feels less like mythic recurrence and more like a strange physical equivalence. The universe does not simply repeat because time loops in a circle. It renews because extreme conditions erase the scales that once kept beginning and ending distinct. This is where the mystery becomes particularly sharp. A cold, empty universe and a hot, dense universe seem, to ordinary thought, like opposite realities. One contains almost no usable energy differences. The other is the source of all later structure. One is the exhaustion of cosmic history. The other is its explosive opening. Yet Penrose's suggestion is that this opposition may be superficial. At the deepest level, once matter with mass is gone and scale loses authority, the cold and the hot may become transformable descriptions of one boundary condition, viewed in different physical languages. If that is true, then the Big Bang is not a singular event emerging from nowhere. It is a disguised continuation of something older, quieter, and nearly erased. There is a certain haunting beauty in that possibility. Everything seen now, every galaxy and every star, every atom in every world, could arise from the ghost of an earlier cosmos that has already passed into emptiness. The present universe would then carry no obvious memory of that predecessor except perhaps the faintest irregularities in ancient radiation and the hidden mathematical fit between final dilution and first intensity. The old universe would be gone in every familiar sense, yet not entirely absent. It would survive not as matter, not as structure, not as preserved objects, but as the condition out of which a new geometry takes shape. Whether this vision is right remains unknown. Many cosmologists remain unconvinced. Standard inflationary models still dominate much of the field. Alternative cyclic proposals face their own difficulties. Observational evidence is contested. Yet conformal cyclic cosmology endures because it touches something central in the mystery of origins. It offers a way to imagine how the Big Bang could be real while not being ultimate. It preserves a physical past beyond the apparent beginning without demanding a simple earlier time inside the same cosmic clock. It lets the universe inherit itself, and if that inheritance is real, then the beginning stops looking like a clean break. It becomes a threshold across which an older emptiness is reinterpreted as a younger fire. The first light of this universe would then be the transformed afterlife of a previous cosmic dusk. The oldest question would remain, but altered. Not why does something come from nothing, but how does an almost nothing, a universe emptied of scale, mass, and structure, become everything again? If any physical trace of a time before the Big Bang still remains, it would have to survive in the oldest light the present universe can reveal. That light is not visible in the ordinary sense. It is microwave radiation, faint and nearly uniform, stretched by cosmic expansion, until it now washes across the sky as a cold afterglow. It comes from a time roughly 380,000 years after the beginning, when the young universe cools enough for electrons to join nuclei and form neutral atoms. Before that transition, space is opaque. Light scatters constantly through the hot plasma and cannot travel freely. Afterward, the universe becomes transparent, and radiation begins a journey that continues to the present day. The result is a remarkable thing, a nearly perfect thermal background filling all directions, a relic field so ancient and so pervasive that it functions as the sky's oldest surviving memory. Yet memory is never simple. Hidden in that almost featureless glow are minute irregularities, and in those irregularities cosmologists search for the possibility that something older than the visible beginning still lingers. The discovery of this background in the 20th century changes cosmology forever, because it transforms the Big Bang from speculation into measurable history. The radiation has exactly the kind of spectrum expected from a universe that begins hot and dense and later cools through expansion. Later satellites refine the picture with astonishing precision. The Cosmic Background Explorer first maps its black body perfection and reveals tiny temperature variations across the sky. Wilkinson Microwave Anisotropy Probe improves the map and sharpens the statistics. Planck, launched by ESA, provides the most detailed full-sky portrait yet, tracing fluctuations so small that they amount to differences of only a few parts in 100,000. These fluctuations matter because they are not noise in the usual sense. They are the seeds of all later structure. Regions slightly denser than average pull more matter through gravity. Over immense spans of time they grow into galaxies, clusters, and the large cosmic web. The microwave background is therefore not just ancient light. It is a map of the universe before stars, before galaxies, before visible structure, when the first unevenness already exists. This alone is extraordinary. The largest structures in the cosmos may begin as almost imperceptible variations in the temperature of ancient radiation. The present universe, with all its complexity, carries within it the magnified aftermath of minute disturbances in a nearly smooth beginning. Inflationary cosmology gives one elegant account of how this can happen. In that picture, tiny quantum fluctuations in a very early field are stretched across the observable universe by a brief burst of rapid expansion, turning microscopic uncertainty into macroscopic structure. The microwave background then preserves the pattern in fossil form. It is one of the boldest bridges between the smallest and largest known scales. A quantum tremor becomes a galaxy. An instability too tiny to imagine becomes the architecture of the sky. Yet the very success of this framework invites a dangerous question. If the microwave background remembers processes from such an early epoch, could it remember even more than standard cosmology allows? The background appears astonishingly uniform, but not perfectly so. Its tiny anisotropies, the small departures from complete smoothness, are expected and necessary. What attracts unusual attention are the features that appear harder to classify. Some are probably statistical accidents, inevitable in any single universe observed from one location. Others may reflect foreground contamination, instrumental effects, or subtle choices in data analysis. Yet the history of cosmology shows that anomalies are difficult to ignore, especially when they sit in the oldest observable layer of the universe. Among the most discussed are unexpectedly large-scale alignments, asymmetries between hemispheres of the sky, a curious cold spot, and other irregular features that do not fit the simplest version of perfect statistical randomness as comfortably as theorists would prefer. None of these has produced consensus that standard cosmology is broken, but neither have they vanished completely into irrelevance. They hover at the edge of interpretation, neither decisive nor entirely forgettable. The cold spot is a telling example. It appears as an unusually large region of lower temperature in the microwave background, first attracting notice in satellite maps and later becoming the subject of repeated examination. One explanation links it to the integrated effects of large structures between Earth and the background, such as a vast underdense region along the line of sight that could alter the energy of photons passing through evolving gravitational fields. Another possibility is that it's simply a rare statistical fluctuation. More speculative suggestions have gone further and imagined that it might be evidence of something far less ordinary, perhaps even a scar from interaction with another cosmic domain. Most cosmologists remain cautious, and for good reason. An anomaly does not become new physics merely because it is intriguing. Yet the cold spot captures the atmosphere of the larger problem. Ancient light contains features that are real enough to measure but slippery enough to resist a final story. The oldest image of the cosmos is not smooth perfection. It is marked, lightly but undeniably, by uncertainty. This is where Penrose's conformal cyclic cosmology makes its boldest observational move. If a previous aeon truly feeds into the present one, then violent events near the end of that previous cosmic age might leave subtle imprints on the microwave background of the new universe. Penrose and collaborators have suggested that supermassive black holes in the prior aeon, especially through their final radiative processes, could produce concentric low-variance circles or related features in the present background. The proposal is audacious because it treats the microwave sky not merely as a record of early conditions in this universe, but as a surface across which messages from an earlier cosmic age might still be written. In ordinary terms, the claim is startling. It implies that the glow filling the sky may contain faint geometrical echoes of things that happened before the Big Bang, or more precisely before the Big Bang as usually understood. The response from the broader scientific community has been mixed to skeptical. Many analyses argue that the claimed circles are not statistically compelling once proper comparisons are made with simulated skies generated under standard assumptions. Others contend that the methods used to define or search for such patterns risk finding significance where none exists. This dispute is not unusual in frontier science. When the signal is delicate and the interpretation profound, every step becomes contested. What matters for the mystery is not that Penrose's specific claims have been accepted. They have not. What matters is that the microwave background is detailed enough, and strange enough in places, to sustain the possibility that deeper history could in principle leave recoverable traces there. The sky's oldest light is no longer just supporting evidence for a hot young universe. It has become a testing ground for questions once thought forever beyond observation. Other speculative scenarios also look to ancient light for clues older than the standard Big Bang picture reveals. Some versions of inflation suggest that bubble universes may form in a larger inflating reality, and that collisions between such bubbles could leave circular signatures or large-scale anomalies in the microwave background. The idea remains highly uncertain, but it shares a pattern with conformal cyclic cosmology. both imagine the background as a surface on which contact with a larger or older reality might appear as geometry, asymmetry, or unlikely alignments. The details differ, but the instinct is the same. If the universe has a past deeper than the ordinary hot beginning, the first place to look is the oldest light that survives. Even polarization in the microwave background becomes part of this search. As light from the early universe scatters in particular ways, it acquires subtle directional patterns that encode information about primordial conditions. Some of these patterns may carry evidence of gravitational waves from the earliest moments, ripples in space-time itself. The hope of detecting such a signal has driven major experimental efforts. A confirmed primordial gravitational wave background would not by itself prove any one speculative model, but it would open a new window onto epochs far closer to the origin than temperature maps alone can reach. The history of this search already contains its own cautionary lesson. Apparent signs, once celebrated as possible evidence for inflation, are later explained largely by interstellar dust within the Milky Way. The episode does not weaken the scientific method, it strengthens it. Ancient light can mislead, and only repeated checking prevents desire from becoming discovery. That caution is essential because the microwave background occupies a dangerous psychological position in cosmology. It is at once richly informative and tantalizingly limited. It reaches astonishingly far into the past, but not all the way. It is detailed enough to suggest hidden stories, but not always detailed enough to settle them. It is a fossil record from a universe still very young, yet not young enough to show the true first instant. This combination produces a peculiar tension. Every increase in precision seems to bring both reassurance and unease. The broad pattern fits known theory beautifully. The finer details leave room for persistent puzzles. The map is stable, but the interpretation of its smallest oddities remains open. The background also invites a more subtle possibility. Even if no obvious circles on scars or collisions are ever confirmed, the statistical form of its fluctuations may still encode information about deeper physics. The exact distribution of anisotropies, the degree of Gaussian smoothness or deviation from it, the spectral tilt, the correlations across scales. All of these may reflect processes from the earliest accessible phase of the universe. In that sense, the microwave sky is not just a photograph, it is a compressed archive. A slight deviation in pattern may carry the fingerprint of quantum gravity, or of a pre-Big Bang phase, or of fields no longer present. The challenge is that many different theories can imprint similar broad effects, and current data, though magnificent, still leaves large regions of possibility alive. The oldest light speaks, but not in a straightforward language. There is something almost unsettling in the fact that the entire sky glows with a relic from near the dawn of the cosmos. Every direction leads into the same ancient bath of radiation. It is everywhere and almost identical, yet not identical enough to be dull. Within its faint mottling lies the promise that the universe can be read backward, perhaps farther than once imagined. The microwave background becomes not merely evidence that the Big Bang happens, but a frontier where the Big Bang may cease to be the first accessible chapter. It carries a paradoxical quality calm in appearance, restless in implication. Its smoothness suggests order, its irregularities suggest unfinished business. So cosmology returns to that dim glow again and again. Satellites map it. Ground-based observatories refine it. Statistical tools dissect it. Theories compete to explain what is ordinary and what is anomalous. Standard cosmology remains strong, and no clean proof of a pre-Big Bang signal has emerged. Yet the search itself changes the meaning of the beginning. Ancient light is no longer treated only as confirmation of one successful model. It is also the nearest wall behind which an older reality might still cast shadows. If anything survives the transition from an earlier cosmic condition into the present universe, it would have to survive in a form subtle enough to cross the violence of the opening. Temperature circles, odd alignments, improbable cold regions, polarization traces, slight departures from expected randomness. These may all turn out to be ordinary once understood fully, but until they are, the microwave background remains more than a relic. It remains a question stretched across the whole sky, a thin luminous veil behind which the universe may still be hiding its first forgotten memory. Once the beginning is no longer treated as absolute, time itself starts to look less like a straight line and more like a structure with hidden curvature. The oldest habit of thought imagines a single cosmic story that opens once, unfolds once, and moves toward a final end. It is a powerful image because it matches human experience. Lives begin and end, fires ignite and go out. Civilizations rise and fall. Memory moves in one direction, but the universe may not be obligated to share that narrative shape. At the deepest scales, cosmology keeps returning to a more unsettling possibility that the cosmos does not begin once at all, but in some sense again and again. Not always in the same way, not always as a simple repetition, but through patterns of recurrence that challenge the idea of a unique first moment. The appeal of cyclic models is easy to understand. If the universe emerges from an earlier cosmic phase, then the first question no longer stands alone. A beginning becomes a transition. A hot young universe grows out of an older state, perhaps one that contracts, perhaps one that thins into emptiness, perhaps one that changes its description so completely that end and beginning become mathematically adjacent. In every version the attraction is similar. A cycle replaces a singular origin. The universe inherits itself. It does not arrive from a total void, but from a prior condition that already contains the seeds, laws, or geometry needed for renewal. This move does not solve every mystery, but it shifts the burden. Instead of explaining why existence appears once from nowhere, it asks whether existence might be self-continuing through forms of cosmic return. One of the oldest cyclical ideas imagines expansion followed by contraction. In that broad picture, the universe begins hot and dense, grows, cools, and eventually reverses under gravity. The reversal leads to a final collapse, often called a big crunch, and that collapse somehow sets the stage for another expansion. It is a compelling picture because it is easy to visualize. The universe breathes in and out, yet modern observations complicate it severely. The discovery that cosmic expansion is accelerating rather than slowing makes a straightforward recollapse seem unlikely in the observed universe, at least under the simplest assumptions. Dark energy, whatever it is, appears to push large-scale expansion onward, not toward reversal. For that reason, many classical bounce models lose favor, or else must be modified with new ingredients. Still, the deeper intuition behind them survives. Even if the cosmos doesn't collapse in the old way, there may be other routes by which one phase gives rise to another. Some bounce scenarios shift the crucial drama to the earlier scale rather than the far future. In these models, the Big Bang is not the absolute start of everything, but the rebound from a prior contracting universe. Instead of beginning at a singularity where density becomes truly infinite, the cosmos reaches an extreme but finite state and then turns outward again. Quantum gravity effects, exotic forms of matter, or corrections to ordinary relativity may prevent total collapse into a mathematical singularity. The universe compresses, but not beyond all meaning. Then a bounce occurs, expansion follows. From within the present cosmic age, the rebound looks like a beginning, even though it is actually the midpoint between contraction and re-expansion. This kind of model carries a clear advantage. It preserves a physical history before the hot early phase without demanding that time itself suddenly emerge from nothing. But it also inherits difficult questions. What determines the conditions of the prior contraction? What prevents disorder from accumulating cycle after cycle? What chooses the properties of the rebound? That last question becomes especially sharp because a repeated universe is not automatically a repeated universe in the strong sense. There are at least two broad possibilities. In one, each cycle differs. New fluctuations, quantum events, or structural variations make every cosmic age distinct. The universe repeats in form but not in content. In the other, the recurrence is exact, or at least close enough that the same large-scale history happens again. The distinction matters. A sequence of varied cycles resembles a family of universes linked by ancestry. A single exact loop resembles something far stranger. A reality that does not merely reproduce new worlds but returns to the very same one. The idea of an exact loop is both austere and unsettling. It suggests that physical reality may consist of a single grand cycle that eventually closes upon itself, though not a metaphorical return but a literal one. The universe runs from its hot beginning through the growth of stars and galaxies into a maximally thinned future, and that future then becomes, by some deep physical principle, the condition of the very same beginning again. Every structure reappears, every fluctuation returns. The same history unfolds not because someone rewinds it, but because the total configuration of reality is cyclic at its deepest level. This is not a popular everyday view of cosmology, yet it emerges naturally once one begins taking seriously the possibility that the end state of the universe and the beginning state may be physically linked more tightly than ordinary linear time suggests. Such a one-cycle picture carries a severe beauty. It removes the need for an infinite regress of earlier and earlier universes, while still avoiding a single unexplained first event. The cycle explains itself by closure. The end becomes the beginning of the same whole. Nothing lies outside the loop. Nothing external needs to ignite it. There is only one continuous reality turning through different phases. Yet this elegance has its own cost. If the loop is exact, then all apparent novelty exists within repetition. Every ancient star formation, every black hole, every fluctuation in relic radiation, every later world, all a part of a structure that has already happened and will happen again not in another universe, but in this one, eternally. The universe would then be both old beyond measure and strangely unchanged in its total pattern. Physics does not currently establish such exact return, but the idea persists because modern cosmology repeatedly uncovers ways in which apparent beginnings may conceal continuity. Penrose's conformal picture offers one path. Certain quantum cosmologies offer another. Some interpretations of gravitational entropy and global geometry leave room for forms of recurrence not yet fully understood. Even without a final theory, a pattern emerges. The more carefully the origin is examined, the less isolated it appears. The beginning keeps behaving like the visible edge of a larger structure rather than a solitary miracle. The problem of entropy haunts all of these models. In ordinary thermodynamics, systems tend toward disorder, or more precisely toward states with more possible microscopic arrangements. If the universe cycles endlessly, why does each new cycle begin in a low entropy condition, organized enough to support complexity and long development? Why is the beginning not already exhausted? This is one of the hardest challenges for any cyclic cosmology. Some approaches argue that expansion and the erasure of meaningful scale can reset the problem in unexpected ways. Others suggest that the relevant entropy is carried by gravitational degrees of freedom that behave differently on cosmic scales than intuition expects. Still others simply do not yet solve the issue convincingly. The point is not that cyclic theories are complete. It is that they are driven by the same pressure that haunts every account of origins, the need to explain why the universe begins in a state so special. There is another reason recurrence remains attractive. A strictly one-time beginning leaves many features of the cosmos looking arbitrary. Why these laws? Why this initial smoothness? Why this particular balance between expansion and structure formation? A cyclic framework can, at least in principle, turn some of these apparent givens into inherited properties. The universe does not choose them once from nothing. It carries them forward from prior states. This does not dissolve the mystery, but it makes the observed cosmos feel less like an isolated exception. The present universe becomes one expression of a larger process whose structure may stabilize certain features across cosmic ages. In that sense, a cycle can function almost like memory. What the universe is now depends on what it has been before, yet memory in cosmology is rarely clean. If there are many cycles, does each one retain any detectable imprint from the previous? The microwave background offers one possible archive, but the evidence remains contested. If there is one exact loop, what mechanism preserves identity across the transition? If there are varied cycles, what determines variation? Are quantum fluctuations enough to make each aeon genuinely new? Does dark energy remain constant from cycle to cycle, or does it shift? Does matter survive only as transformed geometry, or as some subtler informational residue? These are not decorative questions. They are the real terrain on which cyclic ideas stand or fall. The universe may repeat, but the manner of repetition matters more than the slogan. At this stage, a more radical thought begins to form. Perhaps the deepest contrast is not between one universe and many universes, nor between one beginning and repeated beginnings, but between two different conceptions of existence itself. In one conception, reality is fundamentally generative. It produces novelty once and then unfolds it. In the other, reality is fundamentally recurrent. It does not need an outside cause because it is structured to continue through transformations that never quite end. The difference is subtle because both can contain change, complexity, and apparent creativity, but the emotional weight differs. A generative universe feels like a first act. A recurrent universe feels like a pattern discovering itself repeatedly. This does not mean recurrence is comforting. It can be more mysterious than a one-time origin. An absolute beginning is hard to explain, but at least it feels singular. A cyclic cosmos confronts the mind with continuity so deep that the demand for a first event may itself become misplaced. There may be no opening curtain, no first spark, no absolute starting point at all. Instead, there may be only thresholds, transitions, rebounds, conformal handoffs, or closures in a structure too large for ordinary time language to capture. The universe would then resist the most basic narrative instinct humans bring to it. It would not be a story with one beginning. It would be a story in which beginning is only a local appearance. Even the visible universe quietly encourages this suspicion. Galaxies are born from earlier stars. Heavy elements come from older furnaces. Black holes grow from collapsed matter and later shape galaxies in return. Everywhere in cosmic history, apparent starting points turn out to be conversions of prior states. New structure emerges from transformed older structure. Why should the universe itself be the single exception? Why should it alone arise without inheritance? This cyclic imagination feeds on this pattern. It sees in the cosmos a tendency not toward isolated creation, but toward metamorphosis. None of this yet proves that reality is a loop, a bounce, or an endless chain of aeons. Observations still favor caution. Standard cosmology remains powerful. The mechanisms behind recurrence are incomplete. The entropy problem is formidable. The data are suggestive in places but not decisive, and yet the idea persists because it addresses something central in the problem of origins. It replaces the blank wall of a first moment with a deeper continuity. It treats the Big Bang not as the final answer, but as the local face of a larger process. The universe may still begin, but perhaps it begins the way dawn begins, not from nothing, but from a darkness that is already part of the cycle, already carrying the hidden terms of light. If that is true, then the beginning is not alone. Behind it stands not emptiness, but return. Not a silent void, but an older phase whose shape is hard to recognize because ordinary ideas of time and scale break down at the crossing. The universe may move forward, yet still come back. It may produce novelty, yet within recurrence, it may appear to open once, while in fact passing through a rhythm too large for memory. And somewhere inside that possibility lies an unsettling thought that what now seems like one unrepeatable cosmic history could be only one turn of a deeper wheel, or perhaps the same turn seen again, passing from fire to structure to emptiness and then, without warning, back into fire. Recurrence is one way to escape a solitary beginning, but it is not the only one. Another possibility does not send the universe back through its own past. It sends reality outward into uncounted alternatives. In this view, the mystery of origin widens instead of looping. The Big Bang is still a beginning, but perhaps not the only beginning, not the only branch, not the only version of what a universe can become. The cosmos now visible may be just one realized path in a much larger landscape of outcomes, histories, and physical domains. What appears to be a single universe with a single story may instead be one small region in a far wider structure that remains mostly hidden, not because it is far away in ordinary space, but because it is separated by deeper boundaries in law, history, or quantum evolution. The first hints of this possibility arise not from fiction, but from the strange logic of quantum theory itself. At the smallest scales, physics does not describe nature as a collection of objects with perfectly fixed properties at all times. It describes possibilities, amplitudes, overlapping states, and outcomes that become definite only in specific interactions. This does not mean reality is unreal or purely mental. It means the world, before certain kinds of measurement or decoherence, behaves in a way that resists the ordinary demand that one event must take one path and exclude all others from the start. Electrons do not move like tiny planets. Light does not behave purely as a wave or purely as a particle. Systems can exist in superpositions, meaning multiple possible states remain encoded together until interaction with the wider environment forces a more classical appearance. The equations that govern these processes are extraordinarily successful. The problem lies not in prediction, but in interpretation. What exactly becomes of all the unrealized possibilities? One answer, radical and unsettling, is that they are not unrealized at all. The many worlds interpretation proposes that quantum evolution never truly chooses a single outcome by collapsing all others into nothing. Instead, all outcomes permitted by the quantum state continue, each in a different branch of reality. From within any given branch, observers experience one definite result. The others do not vanish. They unfold elsewhere in the structure of the wave function, inaccessible not because they are imaginary, but because interaction between branches effectively ceases. This idea remains controversial, yet it has a severe internal logic. It takes the mathematics seriously and refuses to add a special collapse rule that appears nowhere else in the theory. If correct, it means that reality is far larger than ordinary experience suggests. The universe is not a single stream. It is a branching totality. At first this seems far removed from cosmology, but the connection quickly becomes difficult to ignore. If quantum branching happens constantly at microscopic scales, then the total physical reality may already contain an immense multiplicity of histories. A universe like the present one does not exist alone. It exists as one branch within a vast quantum structure containing countless variations. Some branches differ only in tiny outcomes: the path of a particle, the timing of a decay, the exact pattern of radiation. Others diverge more dramatically over time, because small differences can amplify into different large-scale histories. In one branch, a certain star forms slightly earlier. In another, a galaxy merger unfolds differently. In another, a fluctuation grows or fails to grow. The visible cosmos then becomes a local narrative inside a far wider ensemble. This picture becomes even more provocative when combined with inflationary cosmology. In some models, inflation does not end everywhere at once. While one region stops inflating and becomes a hot expanding universe like the observable cosmos, other regions continue inflating, giving rise to further bubble-like domains. This process can in principle continue indefinitely, producing a kind of eternal inflation. Each bubble universe may share some broad underlying framework, yet differ in important details. Physical constants, vacuum states, symmetry breakings, or dimensional structures could vary from one domain to another depending on how the local region settles. The result is not merely many histories of one universe, but potentially many universes with different deep properties. The multiverse then stops being one speculative idea and becomes several overlapping possibilities, quantum branches, inflationary bubbles, and perhaps even distinct realizations permitted by deeper theory. The reason this matters for the Big Bang is that it changes what the beginning means. A beginning inside one branch or one bubble may not be the beginning of reality as a whole. The hot, dense start of the observable universe could simply mark the local onset of one cosmic region, emerging from a broader background. In that case, asking what came before the Big Bang becomes similar to asking what lies outside a horizon. The answer may not be nothing. It may be a larger generating structure mostly hidden by the limits of observation. The Big Bang would then resemble an opening from the inside, not from the outside. It begins the known universe without necessarily beginning all that exists. There is a certain force to this idea, because it offers a possible explanation for features that otherwise seem oddly specific. The laws and constants of physics appear delicately arranged for complex structure. Gravity is weak enough relative to other forces to allow long-lived stars. Matter survives antimatter by a tiny margin. The cosmological constant appears small enough to permit galaxies to form before expansion tears everything apart. None of this proves design or intention, but it does raise the question of why the universe lands in such a life-permitting range at all. A multiverse provides one possible answer. If there are vast numbers of universes or branches with varying conditions, then it is not surprising that at least some regions allow structure, stars, chemistry, and observers. The present universe would not be uniquely tuned for life by special selection. It would be one of the places where conditions happen to permit complexity, and only such places can later be noticed from within. This line of thought is powerful and dangerous in equal measure. It can make the universe feel less mysteriously special, but it can also weaken the demand for deeper mechanism by explaining almost any observed feature as a selection effect. If everything possible happens somewhere, then nearly any local condition becomes unsurprising. That broad explanatory freedom is exactly why many physicists remain cautious, a theory that allows too much risk saying too little unless it produces specific testable signatures. The multiverse becomes scientifically valuable only where it touches observation, and that is where the search turns again toward anomalies in the sky. Some researchers have proposed that collisions between bubble universes in an inflationary multiverse could leave observable marks in the cosmic microwave background, perhaps as circular temperature discontinuities or unusually coherent features. Others have looked for large-scale asymmetries or statistical oddities that might hint at a boundary with something beyond the observable patch. Nothing decisive has been found. The data continue to support the broad standard picture remarkably well, yet the search persists because the stakes are so large. A confirmed sign of interaction with another cosmic domain would transform the Big Bang from an ultimate beginning into a local event inside a wider reality. There is also a darker and more abstract possibility. The other universes may never interact at all. They may be real in the same broad sense as the present one, and yet forever inaccessible. Quantum branches may decohere so completely that no signal can pass between them. Inflationary bubbles may be causally isolated by expansion. Distinct vacuum states may be separated by barriers no ordinary process can cross. In that case, the multiverse remains physically meaningful but observationally elusive. Reality becomes larger without becoming easier to verify. The cosmos would then possess a hidden excess, a silent abundance beyond all direct reach. The known universe would not be false. It would simply be incomplete in a more expansive way than classical cosmology ever imagined. This hidden abundance changes the tone of the origin problem. Instead of asking why there is one universe rather than nothing, one begins to ask why there is a framework that permits many universes at all. The mystery does not disappear, it migrates upward. Why does inflation occur? Why does the quantum state branch? Why does the deeper landscape of laws, fields, or geometries exist? Why is there a meta-reality from which so many local realities can arise? The multiverse does not answer these questions. It intensifies them by pushing the frontier outward. The first cause retreats into a larger structure, and the old absence returns at a higher level. Yet even as speculation widens, the present universe keeps anchoring the inquiry. Dark matter still shapes galaxies without revealing its identity. Dark energy still accelerates expansion without offering a comfortable explanation. The vacuum still fluctuates. The microwave background still carries subtle irregularities. Quantum theory still describes a world more plural in possibility than ordinary experience admits. These are not proofs of a multiverse, but they prepare the imagination for one. The cosmos already contains hidden sectors, inaccessible components, and layered realities beneath appearance. In such a setting, many worlds no longer feels like an intrusion from fantasy. It feels like the continuation of a pattern already visible, that every time the universe seems close to being fully known, it opens onto another unseen level. If this is the true shape of things, then the darkness between galaxies is not the most profound darkness in nature. The deeper darkness is ontological, a darkness of unrealized or unobserved possibility, a vast reserve of worlds, branches, or domains that never enter direct view. The Big Bang then becomes not the first light of everything, but the local flare of one path among innumerable others. Somewhere beyond the limits of observation, perhaps beyond the limits of interaction itself, reality may be splitting, budding, or unfolding into histories that never meet this one. The present universe would still matter, still contain all known stars and all known life, but it would no longer stand alone. It would be one chamber in a structure too large to survey, one bright fragment in a darkness filled not with emptiness, but with other beginnings. The deeper the search for origins goes, the less the universe appears to follow a single style of behavior. On the larger scales it seems lawful, measured, and almost severe in its consistency. Galaxies do not wander without pattern. Gravity sculpts motion with astonishing regularity. Light bends in predictable ways around mass. Orbital systems form, stars ignite, and cosmic expansion follows mathematical rules that can be traced across billions of years. This aspect of the cosmos invites a deterministic reading. It suggests that reality unfolds through stable laws which, given sufficient knowledge, would allow the future to be inferred from the past. A universe governed this way feels ordered from its foundation, as though each event emerges from prior conditions with deep necessity. And yet this image cannot stand alone. At the smaller scales where particles flicker, decay, tunnel, interfere, and entangle, the universe seems to loosen its grip on certainty. Outcomes are not always fixed in advance in the way classical intuition expects. They come clothed in probabilities. The cosmos is lawful there as well, but not in the same way. It predicts distributions more readily than individual events. It is precise, yet not fully definite. This dual character matters because any true account of the beginning must somehow contain both. Determinism has long held a special power because it fits the human hope that the world is intelligible all the way down. In classical mechanics, if the positions and velocities of all relevant bodies are known, the future motion follows from the laws. General relativity extends this confidence into the geometry of space-time itself. Given the right conditions, one can calculate how matter curves space-time and how curved space-time guides matter. The large universe, viewed through this lens, becomes a structured unfolding. One stage leads to another through necessity rather than chance. The early density field becomes later galaxies. The mass of a star determines whether it ends as a white dwarf, a neutron star, or a black hole. Even cosmic expansion, once the governing contents of the universe are known, follows a definite trajectory. This lawful continuity gives cosmology its backbone. Without it, there would be no reason to trust any reconstruction of the early universe at all. And yet classical determinism begins to blur as soon as the inquiry approaches the quantum world. There the laws do not seem to vanish, but their mode of rule changes. Quantum mechanics does not abandon order. It replaces certainty about individual outcomes with certainty about the evolution of probability amplitudes. A radioactive atom has no clock face that announces the exact instant it will decay. A particle approaching a barrier may tunnel through it with a calculable chance, not a classical certainty. An electron prepared in a particular state does not always reveal the same measurement result in every repetition, even when the setup is identical. What the theory provides is a distribution, a statistical structure that remains exquisitely reliable across large numbers of events, while individual cases retain intrinsic unpredictability. This is not ignorance in the ordinary sense. It is built into the framework itself, at least in standard interpretations. That difference matters for the origin question because it introduces a quiet but radical possibility. Perhaps the earliest conditions of the universe are not completely determined in the classical sense. Perhaps chance, or something that behaves like chance from within the universe, plays a real role in what kind of cosmos emerges. Tiny quantum fluctuations may help seed galaxies. Symmetry breaking may proceed through processes with probabilistic aspects. Inflationary fields, if they exist, may decay in ways that distribute outcomes across regions. Even the imbalance between matter and antimatter may depend on early physical processes in which statistical asymmetries are amplified into cosmic consequences. The present universe would then not be the inevitable result of fixed initial data alone. It would be the product of law working through uncertainty. This combination can feel contradictory at first, but the contradiction may be only apparent. Determinism and probability are not always enemies. In quantum theory, the evolution of the wave function is often described by deterministic equations, even while observed outcomes appear probabilistic. The law is exact, but what it yields at the level of experience is a spread of possibilities. Cosmology may therefore inherit both characters at once. The universe may evolve according to deep, stable principles, while the realized details of its structure emerge through fluctuations and branching outcomes. On large scales, the result can still look astonishingly coherent. Probability does not mean chaos in the crude sense. It means that order may be generated through lawful uncertainty rather than through classical inevitability alone. This has profound implications for how the beginning is imagined. A purely deterministic origin story suggests that once the initial state and governing laws are specified, everything that follows is in principle fixed. Galaxies, stars, planets, and even the broad conditions for life would be latent in the first state as consequences waiting to unfold. A probabilistic origin story allows a different emphasis. The laws may define a space of possible universes, while actual realized histories depend on fluctuations, branching, or random processes within that space. The first state would then not encode one destiny, but many possible continuations. The present universe becomes one outcome among alternatives permitted by the same deep order. This picture naturally connects to multiverse ideas, to inflationary branching, and to certain interpretations of quantum cosmology. But it can also stand on its own. Even a single universe can carry genuine contingency within lawful evolution. There is a subtle reason this matters beyond abstract interpretation. The cosmos appears finely balanced in ways that have long provoked unease. Fundamental constants fall within ranges that allow long-lived stars and complex chemistry. The early universe begins smooth enough for a coherent large-scale structure, but uneven enough for galaxies to grow. The value associated with dark energy seems small enough to avoid smothering cosmic structure before it forms. The asymmetry between matter and antimatter is tiny, yet not zero. In a strongly deterministic view, such features may reflect a deep necessity built into the laws or into a unique initial condition. In a probabilistic or multiversal view, they may instead reflect selection from a broader range of possibilities. The universe looks special not because it must be this way in every possible reality, but because only certain conditions allow complex observers to later ask why things are as they are. The difference between those two pictures is enormous, and present physics has not settled it. Still, even strict determinism carries its own mysteries. If the universe is fully determined from the start, where do the laws themselves come from? Why are these laws, and not others, built into reality? Why do the initial conditions possess the particular shape they do? Determinism can explain how one state follows from another, but it does not automatically explain why the total framework exists at all. In that sense, it can move the problem of origin rather than dissolve it. A universe governed with perfect necessity may still stand on unexplained foundations. Probability does not solve that either. It only changes the manner in which outcomes arise within the framework. The ancient question survives both pictures. Why is there a lawful reality, deterministic or probabilistic, capable of producing a universe? Some of the most daring approaches to a theory of everything aim to reconcile these two modes by showing that they are surface expressions of a deeper unity. The deterministic smoothness of space-time and the probabilistic behavior of particles may both emerge from an underlying structure not yet fully known. String theory, loop quantum gravity, and related frameworks each try in their own way to describe a deeper order from which both general relativity and quantum mechanics arise as limiting cases. None has yet won decisive empirical support, but the aspiration is revealing. The universe may look split between order and chance only because current theories are partial. A more complete account might show how the two belong together, the way wave and particle behavior turn out not to be rivals, but complementary aspects of one quantum reality. There is an eerie beauty in that possibility. The same universe that appears rigid enough to produce stable stars and elegant celestial mechanics may also be loose enough at its foundations to allow novelty, variation, and branching. It is not a machine in the old mechanical sense, nor a chaos of unrelated accidents. It is something stranger, a lawful generator of possibilities. The large structures of the cosmos may be shaped by deterministic equations, while the specific seeds from which those structures grow are quantum in origin. The universe could therefore be both inevitable and contingent at once. Its broad architecture follows deep rules. Its details emerge through fluctuations. Its existence feels like destiny when seen from afar and like chance when examined closely. This tension becomes especially vivid in the earliest accessible phases of cosmic history. Inflation, if real, would take tiny quantum fluctuations and stretch them into the density pattern that later becomes galaxies. The transition from vacuum-like state to hot plasma may involve decay processes with quantum character. Matter surviving over antimatter may depend on subtle asymmetries amplified under extreme conditions. In each case, the laws define what can happen, but the exact realized pattern is not simply copied from a classical blueprint. The universe is composed through lawful openness. A single improbable fluctuation, once enlarged by expansion and gravity, can reshape the future of millions of light years. What appears random at the smallest scale becomes structure at the largest. Probability, instead of being the enemy of cosmic order, becomes one of its hidden architects. This is one reason the beginning resists any single emotional image. It is not only a first explosion, not only a geometric boundary, not only a rebirth from a prior cycle, not only a branch in a multiverse. It may also be a moment, or more than a moment, in which order and uncertainty become inseparable. The earliest universe is lawful enough to preserve deep consistency and uncertain enough to allow a rich unfolding rather than a sterile repetition. Whether that uncertainty is fundamental, merely apparent, or distributed across many worlds remains unknown. But the evidence already suggests that the universe does not choose between order and chance in the simple way human categories prefer. It uses both. The longing for a final theory arises partly from the hope that this uneasy duality can be brought into one coherent picture. Physicists speak of a theory of everything not because they expect a magical sentence that answers all questions, but because the present split between the gravitational cosmos and the quantum world feels incomplete. A deeper theory would not merely calculate new particles or exotic interactions. It would explain how deterministic geometry and probabilistic processes emerge together, how space-time and quantum behavior belong to one fabric, and perhaps how the earliest universe passes from hidden precursor states into the world of expanding matter and light. Such a theory might still leave the largest metaphysical questions open, but it would move the origin story to a new depth, replacing patched boundaries with a more continuous physical account. For now, the split remains. The universe behaves like an ordered whole on one scale, and a field of probabilities on another. Every attempt to understand what came before the Big Bang must pass through that division. A purely classical beginning seems too simple. A purely random beginning seems too empty. Reality appears to stand somewhere stranger, in a region where exact laws generate distributions, where geometry emerges from quantum structure, where tiny uncertainties are magnified into the visible universe, and where the first conditions may be neither rigidly fixed nor freely chaotic. The beginning, then, is not merely a puzzle about what exists. It is a puzzle about what kind of existence the universe has from the start. Is it written? Is it chosen? Is it branching? Is it cycling through possibilities under rules deeper than either certainty or chance? No final answer appears yet, but the closer the search moves to the source, the harder it becomes to believe that the universe is only one thing. It seems, even at its birth, to be both precise and open, both disciplined and unstable, both governed and mysterious. By the time the search reaches its deepest point, the universe has changed from an object of study into a kind of threshold. At first, it seems straightforward to ask how everything begins. The sky is full of structure. The laws appear stable. The expansion can be measured. Ancient light can be mapped. Matter can be traced backward through increasingly unfamiliar states. Empty space turns active. Time becomes uncertain. The Big Bang loses its status as a final origin and begins to look more like the visible face of a deeper transition. Yet after all of this movement, after telescopes, satellites, field equations, quantum fluctuations, dark components, and speculative models of cycles and branching worlds, one fact remains untouched. The universe still refuses to reveal whether its beginning is a first event, a rebound, a transformation, a handoff from an earlier age, or only a local opening inside a reality vastly larger than the observable whole. Knowledge has advanced enormously. The central uncertainty has not vanished. It has become more precise. This precision matters. It is easy to imagine that mystery survives only where science has not yet reached. But the origin problem does not persist because the evidence is thin in every direction. It persists because the evidence is rich and still incomplete in exactly the places that matter most. The expansion of space is real. The relic radiation is real. The primordial abundance of light elements is real. The gravitational influence of dark matter is real. The accelerated expansion associated with dark energy is real. Black holes exist. Quantum fields fluctuate. Particles and forces behave according to patterns of astonishing reliability. None of this is vague. The modern picture of the universe is one of the most successful intellectual constructions ever achieved, and yet each secure result acts less like a closed answer than like a rung on a ladder descending into deeper unknowns. The deeper the climb, the stranger the foundations become. Take the most familiar statement first. The universe is expanding. This is not a philosophical preference or a poetic image. It is a measured fact preserved in the redshift of galaxies and in the large-scale architecture of the cosmos. Run that expansion backward, and the early universe becomes hot and dense. That fact anchors nearly everything that follows. But it does not say what produces the condition from which expansion begins. It does not say whether the earliest extrapolated state is physically real or only the limit of a theory applied beyond its jurisdiction. It does not say whether the hot dense phase is the first state or the first visible state. The standard cosmic timeline is secure as history after a certain point. It becomes more tentative as it approaches the source. Then there is the cosmic microwave background, almost perfectly smooth, slightly uneven, and endlessly suggestive. It confirms that the young universe once exists as a hot opaque plasma. It preserves the density pattern from which later structure grows. It supports inflationary thinking without uniquely proving any one model. It contains anomalies that may be statistically ordinary, or may one day reveal deeper physical stories. Perhaps the cold spot is only a rare fluctuation. Perhaps large-scale alignments are merely the inevitable tricks of small-sample cosmic statistics. Or perhaps ancient light still holds information not yet decoded, hints of processes closer to the beginning than present theory can comfortably handle. The background remains one of the greatest successes in science, and one of the greatest invitations to caution. It says much, it does not say enough. Dark matter sharpens the feeling that the visible universe is incomplete at every scale. Galaxies rotate too quickly at their edges unless additional unseen mass is present. Clusters lens light more strongly than visible matter alone allows. Large-scale structure forms in ways best explained by a hidden gravitational scaffold. Yet whatever this matter is, it has not yielded easily to direct detection. It seems to surround ordinary matter while remaining aloof from light. If even the present universe contains a dominant invisible component still unidentified, confidence that the beginning is already understood begins to look premature. Dark energy deepens this unease further. Cosmic expansion accelerates, as if empty space itself contains an outward pressure or some more exotic property. The simplest mathematical form fits the observations well, but its physical interpretation remains unsettling. The vacuum appears to matter cosmically, yet the scale of its measured influence sits uneasily with quantum expectations. The present universe already rests on absences. The beginning may rest on larger ones, and then there is the problem of the singularity. In the simplest reading of general relativity, tracing the universe backward leads to a state of infinite density and temperature. Yet infinities in physics often mark not a discovered thing, but the edge of a failing description. The singularity may be less a real object than the shadow cast when general relativity is pushed into a regime where quantum gravity must take over. This is why the Planck era stands so powerfully at the centre of the mystery. It is not just earlier than the times that can be described comfortably. It is the place where the known frameworks cease to fit together. Space may no longer be smooth. Time may no longer function as a stable parameter. Cause and effect may not apply in the familiar order. The universe may still possess a definite structure there, but whatever it is not captured cleanly by the theories that work elsewhere with such grace. Out of this breakdown come the major speculative roads, each compelling, each incomplete. Inflation offers a mechanism for smoothing the observable universe and planting the seeds of galaxies through stretched quantum fluctuations. Yet inflation itself raises questions about the field that drives it, the state that begins it, and whether it ends everywhere or only locally. Conformal cyclic cosmology offers a grand bridge between a cold, empty future and a new hot beginning, using the loss of meaningful scale as the hinge between aeons. It is elegant and provocative, but observational support remains disputed. Bounce models avoid absolute singularity by placing a prior contraction before expansion, though they must explain how the bounce occurs and how low entropy is renewed. Multiverse scenarios widen the context and suggest that the Big Bang may be one local emergence among many, perhaps within eternal inflation or quantum branching, but they struggle with direct testability. None of these proposals can be dismissed as pure fantasy. None can yet claim decisive victory. The universe still stands open between them. The entropy problem remains one of the hardest obstacles in the entire landscape. The observed universe begins in an extraordinarily special state, smooth enough to permit coherent large-scale evolution, and structured enough to allow gravity to build complexity over time. Why the beginning is so low in entropy remains deeply unclear. Ordinary systems drift toward equilibrium. The early universe, by contrast, seems to begin in a state from which enormous complexity can later unfold. Any explanation of origins must face this head-on. A one-time beginning must explain why such an improbable state exists at all. A cyclic universe must explain how such a state returns or is effectively reset. A multiverse must explain whether such beginnings are rare, generic, or selected through some deeper principle. The low-entropy past is not a side issue. It is one of the most intimate clues that the beginning is not yet understood. There is also the matter of scale, and the strange way scale seems to dissolve near the deepest boundaries. In ordinary existence, size and duration anchor all understanding. A star is larger than a stone. 1 billion years is longer than a day. But extreme cosmological theories repeatedly suggest that such anchors may not survive the origin. In the Planck regime, space-time itself may be emergent. In conformal cyclic cosmology, the far future and the hot beginning may be joined because size loses absolute meaning when mass disappears. In quantum descriptions of the early universe, what later appears as the vast cosmic web may descend from microscopic fluctuations stretched across unimaginable distances. The visible hierarchy of scales may therefore conceal a deeper unity in which large and small, early and late, are not separated as sharply as they seem. The beginning then stops looking like a point at one end of a line and starts resembling a change of description, a boundary where the categories used within the universe cease to hold. Even the contrast between existence and nothingness has become unstable under scrutiny. The quantum vacuum is not empty in any classical sense. Fields fill it, fluctuations disturb it, forces depend on it, space itself may have energy. This does not prove that something literally arises from nothing. On the contrary, it shows how difficult true nothingness is to define physically. Each time thought approaches absence, physics uncovers another layer of hidden structure. The vacuum is not nothing. Space-time may not be fundamental. The beginning may not be first. The universe behaves as though emptiness is never quite empty, and simplicity is never quite simple. That pattern may be telling. Perhaps the old question is framed too starkly. Perhaps existence does not erupt from absolute non-being, but from states so stripped down, so symmetrical, or so unlike ordinary matter and time that they only resemble nothing from the perspective of beings who live among stars and stones. And yet one must stop before overconfidence. Suggestive patterns are not solutions. The fact that every attempt to reach nothing uncovers deeper structure does not prove that there is no ultimate boundary. The fact that several viable models point beyond the Big Bang does not prove that one of them is right. The fact that the microwave background contains anomalies does not prove hidden aeons or bubble collisions. The fact that quantum mechanics allows many interpretations does not prove many worlds. The correct stance at the frontier is neither disbelief nor surrender, but disciplined openness. The universe has already shown that it can be more surprising than the intuition allows and more lawful than imagination expects. That combination demands patience. Perhaps this is why the origin problem continues to exert such force. It is not merely a technical difficulty left over from unfinished theory. It is the place where every major strand of modern physics meets its own limit. Cosmology arrives with measurements of expansion, relic radiation, and structure formation. Particle physics arrives with quantum fields, symmetries, and vacuum fluctuations. Gravitation arrives with curved space-time and singular limits. Quantum theory arrives with probabilities, branching interpretations, and the deep puzzle of measurement. All of them point toward the beginning. None of them fully owns it. The source of the universe sits at the intersection of successful frameworks that still do not quite become one. So the Big Bang remains both true and incomplete. True as the name for the hot, dense early phase from which the observable universe expands and evolves. Incomplete because it does not finally explain what prepares that phase, what underlies it, whether it comes after something older, whether it is one among many beginnings, or whether time itself is born so near that the question of before dissolves into a more difficult one. The phrase may describe the opening of the known cosmic drama without revealing the architecture backstage. The universe has not contradicted the Big Bang. It has grown larger around it. In the end, or perhaps not the end, the deepest impression is not of failure but of unfinished depth. The stars still burn, ancient light still crosses the sky, space still stretches, black holes still evaporate in theory across futures too long to imagine, quantum fluctuations still trouble the vacuum, dark components still shape what can be seen without showing their faces. The universe remains intelligible enough to study and strange enough to resist conclusion. Somewhere behind the first visible light, behind the earliest plasma, behind the fading of scale and the soft collapse of ordinary causality, something waits that present physics can circle but not yet enter. Whether it is a prior aeon, a bounce, a branching horizon, a deeper vacuum, an emergent geometry, or something not yet conceived, it keeps the beginning open, and as long as that opening remains, the first moment of the universe is not a closed answer at all. It is the oldest unsolved invitation in the cosmos. What remains, after all the theories and all the measurements, is not a final answer, but a widening edge. The universe still appears to emerge from a hot and brilliant beginning, yet that beginning no longer feels simple. Behind it may stand a quantum vacuum that is never truly empty, a deeper structure from which space and time themselves emerge, a previous cosmic age fading into silence, a rebound from collapse, or a vast field of parallel realities unfolding beyond every visible horizon. Each possibility begins with something real, ancient light, expanding galaxies, invisible matter, accelerating space, fleeting quantum events, and each one leads, step by careful step, into a region where certainty thins and mystery grows clearer instead of smaller. In that sense, the greatest discovery may be that the universe is not only stranger than once imagined, but stranger in layers. Every answer reveals structure beneath structure. Matter is not fundamental enough. Empty space is not empty enough. The Big Bang is not final enough. Even time may not be deep enough to hold the first true beginning. The cosmos continues to offer evidence, but it guards its source with extraordinary subtlety, leaving behind patterns, traces, and possibilities rather than anything like a simple confession. So the story does not close with a solution. It settles into a quieter wonder. Somewhere beyond the first light, beyond the first atoms, beyond the first stable particles, reality may still be unfolding in ways no human mind has fully named. The universe may have begun once. It may have begun many times. It may still be beginning in places forever hidden from view. And in the vast darkness between what is known and what is merely hinted at, the oldest question remains undisturbed, waiting patiently among the stars,